Good evening. I welcome you to this live interaction session. Today, we'll be discussing the contents of week three. So, we'll get started. So, before I start, are there any questions that you have? Today, I'll try to, as you had recorded your feedback, I'll try to conduct it in Hindi and English both. But other than that, any questions? If there are none, we'll get started. Okay. Okay, so today, essentially, we'll be dealing with the topic of trusses and a bit of beams. So let us take a look at the first question. So the first question asks, which of the following statement is correct regarding purlins? So just to brief about what purlins are, essentially if I take a member like that and let this be a truss, and then I have this arrangement, for example. So in actual roofs, essentially we'll be having structures like these, and then we will be having members which connect them like that. So over which we will have some sort of an arrangement. Yeah, yes, good. Yeah, thank you. So we'll be having arrangements like that over which there'll be some way to load this. So there'll be loads applied to this, something of that nature. So these elements essentially behave like beams, which is they take transverse loading midway within the span also, and they successfully deliver it to these joints of the trusses. So when we actually see a truss which has loads that are applied, those loads are getting transferred to that truss using these members only. For example, the first beam, if we see, as we have loaded here, so if I were to just take this thing out, if I just take this thing out, this will have some reaction like that. And by Newton's third law, that reaction will get applied onto the joint of the truss. So essentially, this behaves like a beam, a bending member, which by bending it transmits the load onto the joint of the truss, and after which trusses we can analyze separately. So that is the entire essence of this. So these are generally called purlins or rafters. So our question pertains to these members. So let us look at the options. The option says purlins are also called rafters that are beams in bending which carry the wind loads and weight of the roof. Yes, as we discussed, this is correct. The length of the purlin is small as compared to the cross-sectional area. Essentially, one thing we should note that beams are members, slender members. When we go to higher studies, we'll be dealing with something called deep beams, but that is quite specialized. But in general, beams are quite slender, meaning slender means that the cross-sectional area is much smaller, or the least lateral dimension is much smaller than the length. So if I have a rectangular beam like that, let me. So in case of if this had a cross section like that, and we extend it like that, so this dimension essentially, call this, let us say, h, and this dimension that goes is L. So L by H would be much greater than 1, because it is a very slender member. Essentially, the cross section has very less dimension as compared to the length of the member. So these are slender members. So these are how beams behave essentially. So the length of the purlin is small as compared to the cross-sectional area is not correct. These are actually slender members. So these are supported only at the joints of the truss. So the main purpose of using a truss, except that it is quite economical and it is efficient in load carrying, is that we want to cut down on the middle joints. So even if you look at the many bridges that are there which use truss, their spans will be quite high. The reason is, in order to cut down intermediate joints, intermediate supports, we can have two end supports and try to support the truss, and truss is quite capable of having this. So essentially, when we see that purlins, these connect the joints of trusses, and why only joint, that we will be seeing in the next question. That has something to do with it. Why the trusses should be loaded only at the joints. But when purlins are supported by trusses, these are essentially connected to the joints where they will deliver the reaction, after which we will have a planar truss of sorts with the load supplied, which we will analyze further. So this is correct. They are designed to withstand only axial, only tension and compressive loads. So we know that truss member is an axial member, as we discussed in the previous session also. Axial member means it can take either compression or tension. It cannot take any bending. But as we saw, purlins essentially take the transverse load, bend, and they deliver the reaction to the joints of the trusses. So these are bending moments and shear force. These get delivered in the form of bending moment and shear force. Load transmission happens in that form. So these are not only tension and compression members. In fact, if anything, they are tension and compression clubbed into a section. So in a beam, if we see, the top portion will be in compression, the bottom portion will be in tension if it is subjected to one particular kind of loading, and the central core will not participate, which is also discussed in the lectures. So this is not correct. So essentially 1 and 3 are correct. So we'll tick option 1. This is just a slight detour about beams before we get started full on truss analysis. But in order to get the global picture as to how beams and trusses are arranged to make structures, this was asked, and it is also discussed in the lecture. Overall, we have two trusses which are supported by beams. Similarly, a truss bridge, if we see, it has floor beams which will deliver the reaction to the truss at its joint. So after getting the global picture, we go into the analysis of truss beams separately. So that is the idea behind this. So if there are any questions here, you please feel free to ask and I'll try to take it there. Is it clear what we discussed? Okay, I hope this is clear. And since in the previous sessions, some people had asked that I also explain it in Hindi. So as and when there is a need, I would request you to please raise it that I need to explain it in Hindi, in which case, yeah, yes, please. Yes, Mr. Shubham, go ahead. What is your question? You have any question, Mr. Shubham? Please, if no, okay, okay. So what I was saying was, since there were some people, attendees who were asking me to explain it in Hindi, so if there is a need for that, I would request you to please raise that, but explain in Hindi. Okay. Yeah, so that is what I'm saying. So if you need me to explain it in Hindi, you please come forward and ask, because I will then contain my explanation to that portion alone. Because the entire session I cannot conduct it in fully Hindi. So I will conduct it in English, and as and when there is a question, or if you want me to explain one particular question in Hindi, that I'll do. Okay, so okay, let me just briefly explain. क्या है कि सर ईएस क्वेश्चन को एक बार इस क्वेश्चन को एक बार हिंदी में समझा दीजिए. ओके, देखिए हम अभी ना ओवरऑल पिक्चर देख रहे हैं कि ट्रस और बीम्स ये सब असेंबल कैसे होता है. जैसे मान लीजिए रूफ है, तो रूफ स्ट्रक्चर्स में क्या होता है कि ऐसे ट्रस होते हैं दो. अब उन ट्रसेस को इन बीम्स के थ्रू कनेक्ट किया जाता है उस ट्रस के जॉइंट पे. क्यों? क्योंकि इसके ऊपर जैसे कोई, अब इसके ऊपर कोई ऐसे शीट बिछा देंगे जिसके ऊपर लोड आएगा, स्नो लोड या कोई भी लोड, विंड लोड, तो उस लोड को ये जो ग्रीन कलर के बीम्स हैं, इनको राफ्टर या पर्लिन बोलते हैं, ये लोड इनके ऊपर डिलीवर होगा. जैसे यहाँ पे दिखाया हुआ है, एक पॉइंट लोड लगा, यूडीएल लगा, जैसे भी कोई भी जनरलाइज लोड उसके ऊपर लगेगा, और वो दैट दिस पर्लिन इट इज अ बीम, तो वो बेंड करेगा. बेंड करके, जैसे अभी हमने देखा था कि मान लीजिए इसको हम अलग करते हैं तो इसका फ्री बॉडी डायग्राम कैसे होगा। यहाँ पे कोई लोड लगेगा, यहाँ पे कोई एक रिएक्शन लगेगा, जो भी मैग्नीट्यूड का है वो हम देख लेंगे, और वही न्यूटन्स थर्ड लॉ से इस जॉइंट पे लग जाएगा। तो हम जब कोई भी क्वेश्चन देखते हैं, एक ट्रस हमें दिखाया होता है प्लेन में जिसमें जॉइंट पे लोड लगा होता है, तो वो लोड आता कहाँ से है ये समझने के लिए ये क्वेश्चन पूछा गया है कि वो लोड एक्चुअल में आता कहाँ से है। क्योंकि हम तो पीस बाय पीस एक्सप्लेन करते हैं, स्टडी करते हैं, बट ओवरऑल वो बन के कहाँ से आता है। जैसे ये एक एग्जाम्पल हो गया कि रूफ का, हमने देखा कि दो ट्रस है जिसके बीच में हमने पर्लिन दिया हुआ है जिसके ऊपर लोड आएगा और वो डिलीवर होगा। तो उस पर्लिन के ऊपर ये चार क्वेश्चन थे कि ये दीज आर आल्सो कॉल्ड राफ्टर्स, जो बेंड करते हैं और वेट ऑफ द रूफ को ट्रस पे डिलीवर करते हैं। तो ये सही है। और क्योंकि ये स्लेंडर मेंबर है तो इसका क्रॉस सेक्शनल एरिया इसके लेंथ से काफी कम होगा। तो ये स्लेंडर मेंबर, सेकेंड ऑप्शन जो बोल रहा है वो स्लेंडर मेंबर नहीं, डीप बीम्स की एसेंशियली बात कर रहा है, इस वजह से वो सही नहीं है। तीसरा है कि ये खाली ट्रस के जॉइंट पर ही सपोर्ट होता है, और ये क्यों होता है ये हम अगले क्वेश्चन में देखेंगे, जॉइंट पर ही क्यों होता है। और ये जब हमने शुरू ही ऐसे ही किया था कि ये बेंडिंग मेंबर है, कि ये बेंड होके लोड को डिलीवर करता है, तो ये टेंशन और कंप्रेशन खाली नहीं लेता है, ये बेंडिंग और शेयर फोर्स लेता है, तो इस वजह से ये ठीक है। तो मेरे हिसाब से आई होप दैट दैट इज क्लियर। So with this, I'll just move on to the next question. Which of the following is our necessary condition imposed on the members of a structure for it to be idealized as a truss? So what this is asking is, we have a truss, let us say, some generic truss with which has some supports and then some load applied. So for this to be qualified as a truss, for this structure to be qualified as a truss, what is it that these members should essentially follow? There are some constraints that this member has to respect in order for it to be analyzed as a truss. So the main idea behind truss is that these are made up of members that are axial members, as we saw here. These are axial members, meaning they can take only tension or compression or no load in some particular configuration. So they cannot bend. So with that background of understanding, if we look at these options, members need to be straight. So let us see if a member is curved, what happens. Now we have noted that truss members need to be axial members, meaning forces applied through the axis of the member. So for example, if I have a curved member like that, and then I apply a load, or first let me take this itself. Okay, this is a member, and then I apply it with a load like that. So this is a two force member, I can see. It is under compression. Now the same thing, if I were to replace, let us say I take the same thing, but this time I put an inclined member or a curved member like that. So what happens now is, let us say I try to draw the free body diagram. I take a section somewhere, I take a cut here, and I draw the free body diagram for the rest of the portion. So I take that. So this is in equilibrium, so this has to be balanced, which means it has to be balanced by a force like this. Now if we see, the axis of the member at this point is pointing something like that. So if we resolve this force into its axis, we will also have another force. For example, let us say that the axis is like this. So what will happen is, there will be two forces which make up the actual force. What this means is, because of these two forces, it will not undergo only axial force, it will also undergo some shear. So it will no longer be a two force member. Essentially, it will also be transmitting shear, which is why it cannot be analyzed as a truss member. Members necessarily have to be straight. Okay. Now member axis must be concurrent at the joints. So this is also discussed well in the lecture. For example, if I take this and I just take that joint. Let us say that I have applied some load. Now, if in the case that this is not a concurrent force system, essentially the resultant moment will not be zero. In which case, these moments will also get transferred to the members, which is why we cannot have a force system, a joint, where the members are not connected in such a way that it forms a concurrent force system. Because non-concurrent force system supports a moment. And truss, we have seen it; these are only axial force members. So this is where there is a need that these need to be connected concurrently. So that is also correct. Members must be loaded at joints only. So let us say that I take the same truss and instead of putting the load here, I put this load somewhere here. So what will happen at any section? It will start behaving like a beam instead of a truss. So this is beam behavior. That is why we cannot have the loads applied at somewhere midway in the member. We essentially only apply this at the joints. At the joints. So one might ask that if there is self weight of the member. For example, there is a long member which is made of steel, so it has some weight on its own, and that will definitely be applied at each and every unit of its cross section. In that case, what we will do is we will lump up the total mass and then distribute it equally among both the ends. For example, if this member, if this I'm sorry, if this member weighed some 5 tons, let us say, so we will equally distribute that weight as 2.5 tons and 2.5 tons to the ends and be done with it, be done with the analysis. Essentially, there is a slight rotation and slight moment that the truss members attract, but for all purpose of analysis, we ignore that. Moreover, the applied loads are such that they are the weight, if you account, it will be a minuscule portion of the actual loads that are being carried by these members, which is why it is immaterial. So yes, the members must be loaded at joints only, and the members must not be continuous over a joint. So what happens is, if we have a member like that, for example, in the same very truss, if we had the total member like that, and then midway we just connected a gusset plate and gave, so this will also violate the second condition, because this essentially won't be a joint. The joints of this member are at the ends, at the supports only, but we are loading it somewhere midway by giving it a connection, which is why this is a condition that has to be met. No member has can be continuous through a joint, which is why in convention, even in the lecture, it is explained that when we draw a truss, we should put uh, holes like this, essentially indicating the pins, so that we don't confuse a member to be continuous throughout the joint. If we don't provide this, there could be an ambiguity whether these are continuous through the joint or not. which is not permissible in the case of truss analysis. So I hope that this is clear. If there are any questions, please go ahead and ask. Otherwise, I'll move on to the next question. Is it clear? Okay, I take it that this is clear. So I'll move to the next question. Let me put this thing here. Which of the following numbered members are in compression in the truss loaded as shown? And we have to answer it in one specific fashion. That is fine, that we will see. So first we have numbered members 1, 2, 3, 2, 1, 2, 2, it goes up till 11. And then it is loaded with a load here. And the internal forces have been shown in one particular fashion. And we have been asked, identify which of the members are in compression. So here we need to understand one thing. Let us say that I have a member like that. Okay, so let us say this is a truss member and this has a connection over here. The pin over there. The pin is over here. So what I'll do next is I'll separate out the pin. Initially, let us say that this member 1, let us say it is in compression. So this is how it will look, that it is in compression. So this is also explained in detail in the lecture, but anyway, I'll just go through this. So if there is a pin and I put the pin here, I just take the member alone. So essentially the pin would be pushing on the member. पिन उस मेंबर को कंप्रेस करेगा, तो इस वजह से इस जगह पे आपका कंप्रेशन लगेगा इसमें. The member will be in compression and the pin, if we see from Newton's third law, pin will have the force applied like that. मेरे ख्याल में ये समझ में आ रहा है. जैसे एक मेंबर है जिस पे कंप्रेशन लग रहा है, मैंने पिन को अलग से हटा दिया और मेंबर को अलग से दिखा दिया. ये ग्रीन जिसमें हाईलाइट है वो वाला पिन है. तो व्हेन मेंबर इज इन कंप्रेशन, हमने देखा कि एक फोर्स उसको कंप्रेस कर रहा है एंड देन वी हैव a force, an equal and opposite force that is getting applied onto the pin. So this is in case of a compression, and we are able to see that the force is on the same side of the member. दोनों ही right side पे लगा हुआ है. For example, if I take that pin here, this is the member side and this is the other side. So I'm able to see that force is on the same side of the member and applied in this direction. So far so good. This is for the case of a member in compression. Now if I take the member to be in tension instead, what happens? So let me just move it over here and I have the tensile force here. So what would happen is it will get pulled at this end, the other end of the pin, not this side but this side. It will get pulled like that. And if I see the free body diagram of the pin, I would essentially have a force like that on the left side, on the other side. So now if I have to have a convention, it has to be represented. For example, vectors, when we compare two vectors, it has to be with the same basis. Similarly, for truss analysis, we will follow a convention that we will we will rather consider forces to be on the same side of the member. Same side of the member means if I have a line like this is the member side, this is the other side. So if I have to put this in the member side, I can invoke that principle of transmissibility and I can put the force here with respect to the pin. I hope this is clear. So when we do, this member is in compression. And this member is in tension. So with this understanding, if we take here, we will be taking the pin as the reference, and whatever forces are pointing away from the pin. So this is pointing away from the pin. We can see that the member would be in tension. Similarly, when it points towards the pin, the member would be in compression. So with this convention, if we try to attempt this problem, we are able to see that at this joint, force is pointing towards the pin. So this is under compression. This member is under compression. Equal and opposite दूसरे end पे भी होगा, क्योंकि तभी वो उसको दबाएगा. That is how it will get compressed. Now, so we have identified कि one compression में है. Similarly, 2 में भी we are able to see कि pin के towards force लगा हुआ है. तो 2 भी compression में है, 3 भी compression में है. 4, अगर हम 5 देखें तो हम देख पा रहे हैं कि we are able to see that force is pointing away from this joint. Similarly, if we consider this pin, the force is pointing away from it. And we saw when force points away, it is in tension. We saw it here with the explanation, right? So 5 is in tension, 6 is in tension, 7 is in tension. Let us consider 8. 8 would be pointing away from the joint. So this is also in tension. 9, there is nothing marked. Essentially, it's a zero force member. We'll come to that discussion later. In member 10, we have the force pointing towards the joint. So essentially, this is in compression. And 11, we can see that it is pointing away from the joint. So this is in tension. So in the question, we have been asked to collate and report all the members that are in compression. And we have to do it in ascending order without spaces. So for example, if 6, 4 and 11 were found to be matching the criteria given in the question, then we should report the answer as 4611. This is for computerized checking. I suppose you can bear with that. So in this slide, if we look at the answer, what would it be? We have 1, 2, 3, 4. Then what else is in compression? Then 10 is in compression. Member 10 is in compression. So the answer would be this. Is it clear? Are there any questions here? So साथ ही में मैंने थोड़ा हिंदी में भी समझाने की कोशिश की थी, मेरे ख्याल में वो क्लियर है आपको. अगर उसे ज़्यादा ज़रूरत पड़ रही है तो आप पूछ लीजिएगा बीच में रोक के. I take it that this point is clear. So if it is, then yeah, okay, great. So I'll also try to switch between English and Hindi, but in case I forget or you show the diagram once again. This is the diagram. Which diagram? This question diagram or which diagram you want to see? Okay, all right. Okay, so I suppose this is clear. So we'll move on. Let us look at the next question. Consider the planar truss loaded as shown. So we have a truss like that. We have a pin joint here and we have a pin joint here, and it is loaded on the top with a force pointing that way. Okay. So the total number of unknown forces and reactions in the loaded truss assembly are how many is what is asked. So we know for a pin R is 2 for a pin, because essentially it arrests translation in both directions. So we are able to see here that both the ends are pinned. It is not that it is having a roller here. It is not so. It is also having a pin at that point. So essentially our total number of reactions into two pins. So R is 4. Let me call this RP and write that as R. So R is 4 here. And what else is left? The member forces are left. And we know why we count the number of members, because each member has only one unknown, which is the magnitude of the force. Essentially, tension and compression can be combined into the same thing, because we will initially assume it to be in tension. And if it doesn't come out to be so, the answer will come out to be negative, which will reflect on the need for us to reverse the direction. So this we discussed in the last session also. So essentially we need to count out the members. So we have one. Another thing is, as we saw, if this was a single member, there would be no pin provided here. This is why it is essential to provide pins at the end, so that we qualify that this is a separate member and this is a separate member. So I hope that that is clear. So we have 1, 2, 3, 5, 6, 7, 8, 16 and 17. So the number of members are, sum total of the members are 17. So if we know this, what is it that we need to report? The total number of unknown forces and reactions for the loaded truss are M plus R, which is 21. Okay. Now let us look at the joints. So we have 1, 4, 7 and 9 joints here. So at each joint we have two equilibrium equations. Why? Because in a plane we have generally three equilibrium equations, which is, if I consider this to be the xy plane, I have sigma fx equaling 0, y equaling 0 and sigma m z equaling 0. But at each joint, since it is a concurrent force system, which is a constraint to be respected for us to be going for truss analysis, this gets trivially satisfied, which is why we have at each joint only two equilibrium equations, two independent equilibrium equations, which means 2 into number of joints, which gives us 18 equations. So we can write 18 equations, but we have a total of 21 unknowns. So this is statically indeterminate. So the question says which one of the following is true. So it is statically indeterminate. So I hope that that is clear. So for the same truss, how many zero force members are present in the loaded truss assembly as shown? So there are conditions for zero identification of zero force members. Essentially, if I have or okay. Let us say that I have an assembly like this, which has three members connected at a joint. And this is a cut section. For example, I have cut it something like this. Okay, so similar to that, I have cut this out from some other truss. So this is just a joint where we have exposed the forces. And if it so happens that two of them are collinear, then if I consider this to be some f, this is f1, call this f2, and let us call this f3. And let me say that this is the xy plane. So if I call this angle theta, some theta, general theta. So sigma fy equal to 0, if I do, it will give me sigma f3 cos 60 or sine 60, sorry, sine 60 equal to 0, which gives me F3 equals 0. So we need not go through this exercise. We can clearly conclude something based on this, that if there is a joint which has three forces or other three members connected, out of which two are collinear, and it should be free of any other external forces. Because if I have a force here applied, the applied force, let us say it is 2 kilonewton, then we can see that the 2 kilonewton will appear here, minus 2 equal to 0. Then it will no longer be 0. So the condition is that it has to be free of any force to start with. So if we have a configuration such that there are three members connected at a joint, out of which any two are collinear, then the force in the third member is 0. So this is one condition to identify zero force members. And why we identify zero force members? To cut down on our analysis. So we can, for the purpose of analysis, we can remove them from the truss and do the analysis a bit quickly. So this concludes from here. Okay. Now, if I have next, let us say I have a joint like that, which is not loaded, but it is taken out of some configuration. Can I conclude something about this? All I can conclude, if I call this, say, F2, and I call this F1, let us say. So sigma Fx, I'll just rotate this a little so that it appears in the x direction. Okay. So if I take sigma Fx, it only gives me F1 equal to F2. It does not say anything about either one being 0. So only from the rest of the analysis, if we get that one of it is 0, then it follows that the other one would be 0. Otherwise, we cannot say anything about a joint which has two collinear members. However, things are not so when we have a joint which is not loaded and it has, uh, let us say this is the case. If I have the force system like that, such that at this joint, the members, joint is not loaded, and I have F1 like that and F2 like that. So for this particular case, or rather for this general case, this being a particular case of this, for this general case, we can see that if we apply sigma Fx and sigma Fy, both would come out to be 0. F1 equal to 0 and F2 equal to 0. So from this, again, we can deduce one more condition, that if there is a joint where there are two non-collinear members and that joint is free of any force, in such a case, both the members would be carrying 0 force. So with this background, if we look at our truss, firstly, are there any joints where there are only two members connecting? There is only one joint we can see where there are only two members that are connecting. But this joint is not free of load. We can see that it is loaded like that. So the condition doesn't get satisfied. So we can no longer conclude that these two are, in fact, those would be carrying force. And there are no other joints where there are three forces, three members getting connected, out of which two are collinear. Essentially, if we see this joint, although these two are collinear, when we cut this, we will be exposing forces like that. So we'll be exposing forces like that. So we have more than three forces there, although two of them are collinear. So we cannot conclude anything out of this. This has to go through the formal route for analysis, and probably all of them would be carrying some force. So in that light, if we see there are no joints which essentially connect three members, so that condition also doesn't get satisfied. So there are no zero force members in this analysis. Is that clear? Are there any questions? If there are, please feel free to ask. I take it that this is clear. और अभी मैं फिर से बता देता हूँ आपको, अगर जरूरत पड़ती है आपको ये हिंदी में समझाने की, तो आप बोल दीजिएगा, मैं तब समझा दूंगा. Otherwise, I'll move on to the next question if things are clear. Okay, so I take it that this is clear. So let us move on to the next question. Okay, thanks. So we have a planar truss which is loaded as shown. At one end we have a pin support, and at the other we have a roller, and we have been asked to report the answers in what particular fashion. If your calculator answer is 7.86, report it to be negative if your answer says that the member is in compression, and report it to be positive if you find that to be in tension. So what are the things that we need to find out? The magnitude of support reaction at joint A, ये जो joint है, यहाँ पे magnitude of support reaction in kilonewton we have to ask, and force in the member Kj in kilonewton, force in the member EF, which is Kj and EF. Kj is one is this member, so we need to report the reaction at A. We need to report that member force, and EF. Okay, so let us see how to proceed about doing this problem. First step is, let us find out the reactions. So let me copy this and put it here. JKL. So this is joint J, K, L, and I have A. So what I have essentially done is I have removed the supports. So once I have removed the supports, we will be replacing the effect of that support with reaction. So call this XY. Let this be in the XY plane. So I have AY, and let me take this AX to be pointing like that. AX. And we know that at I there is a roller support, so it will just be IY. Okay, and each of these is 2 meters. In the question it is given. So each of the smaller segment is 2 meter. Now there are two ways to go about solving this question. But first, let us get the reactions out of the way. So if I do, what are the equilibrium equations available for this body as a whole? It must be clear that for the body as a whole, we have sigma fx equaling 0, sigma fy 0, and sigma m z. But mostly we will drop that z, because we take it once we do planar analysis, it is invariably about the z axis, considering the plane to be xy. So we will generally drop that z. So it must be carefully noted that these three equations are available in the plane invariably. It is only that when we go to a joint, the third equation doesn't mean anything, doesn't give us any useful result, because it is just 0 equal to 0 because of a concurrent force system. That is all. So these three equations are available for us to find out these three unknowns. So there are three equations and three unknowns. globally. So it is a determinate problem. So let us go about solving this. So if I apply sigma fx equal to 0, what is it that I get? I have a force Ax pointing in the x direction. And then are there any other horizontal forces that are applied in the x direction? There are none. So essentially, this gives me sigma fx equal to 0 gives me Ax as 0. Okay. Now I can take sigma fy equal to 0, which gives me ay plus iy minus all these other forces are pointing in the negative y direction. So we will have to subtract that. So we may well add them together. So we have three twos and we have four ones. So we have three twos and four ones equal to 0. Why? Because there is an equilibrium. So this gives me ay plus iy equal to 10. Okay, 10 kilonewton. Now we can impose the third condition of equilibrium, which is sigma m equal to 0. So as we discussed, sigma m can be taken about, moment can be taken about any point. We are free to do that. Only we will take it about a point which will make it rather simpler. So if let us say I take moment about this I, so I can eliminate the contribution of Iy because m is r cross f and r goes to 0. I also see that this, sorry, I can also see that this Ax passes through I, so it will not have any contribution. So at once I can find an equation that is only in terms of Ay, in which case I can solve for it easily. And this being the xy plane, we can see that any anti-clockwise moment would have its axis parallel to the positive z-axis. So in equilibrium condition, when we are applying, all anti-clockwise moments will be positive and all clockwise moments will be negative. So if we see, Ay will have a clockwise contribution onto I. So let us take this about point I, or pin I should say, pin I. So this will be minus Ay into what is the total distance? It is 312 plus all these moments, all these forces are pointing downwards. So all these will have about I, all these forces will have anti-clockwise contribution, which means all these will be positive. So let us try to see that. So the force at point B is 1 kilonewton pointing downwards, and this will have a lever arm of 12 meters. So it is plus 1 into 12. So let me not write separately, let me club them together. For the force 1, for this force 1, 12 is the contribution of this. So we have accounted for the contribution of this, the force applied at B. Then we have a force applied at 1 kilonewton is applied at C, at F and G. So what are the respective lever arms that we need to sum up? This will be 1, then this will be 1, then this will be 1. So what is the sum total of this? We have 12 minus 2, which is 10. So I need to add 10 plus sum of this is 4, and then I have one more 2. 4 plus 2. Now coming to the 2 kilonewton force. 2 kilonewton force, we can see that it is applied here and here and here. So for this force, the lever arm will be this much, which is 8. For this force, the lever arm will be 6. And for this force, it is applied at that very point. Using principle of transmissibility, we know I can shift that force here and it will cause the same external effect, which means it will not have any contribution. So for that force, what I need to do is, one is 8 and the other is 6. So let us put that 8 plus 6 equaling 0. So we have accounted for everything now. So can we calculate AY from here? AY comes out to be 12 plus 10, 4 plus 2 plus 2 into 8 plus 6 by 12. So we get AY as 4.67 kilonewton. I hope this is clear. What I'm doing is clear. So now we have this equation 1, which says that both AY and IY have to sum up to 10. So if AY is 4.67, then IY becomes 4.67, 5.33 kilonewton. Okay. So what we have done is, let me take this thing again. Copy. I, J, K, L. So we have found this to be 4.67 kilonewton and this to be 5.33 kilonewton. Now comes the actual analysis. So there are essentially there is only one analysis in a way. If you say it is to cut sections. For example, if I cut this section, that is I pass an imaginary cut through that. Or let me take this original truss. Let me go here and cut a section like that. So essentially what this section does is it will expose the unknown forces. So I have, this is actually a dimension line. This is a dimension line. So I'll have a force like that. I'll have a force like that and one like this. So when I cut a section, cutting a section is equivalent to exposing the unknown forces, unknown member forces. Now, if I cut the section at one joint, we know that at a joint it is a concurrent force system. At a joint we have concurrent force system. Which implies that we have only two equilibrium equations that will give us useful answers, namely sigma fx equaling 0 and sigma fy equaling 0. And mind you, we are speaking only about planar trusses as of now. So at a joint, we have only two unknown, two equilibrium equations, which means we can at best solve for two unknowns at a joint. So if I were to take a joint which has three forces, for example, if I look at this, the same, okay, let me take this example. If I take this section, I'm able to see that I have exposed three forces now, in addition to the reaction. So this doesn't help. Taking a section like this wouldn't help. So we have to start our analysis only with a joint which has only two forces. For example, if I take this, let us say I cut a section like that, and then I put it here. So I'm able to see that I have exposed two forces. And at that joint, since it's a concurrent force system, I have two equilibrium equations. I can uniquely solve for them, provided the geometric constraints are known and this force is known, which would be the case. So this implies that method of joints, that is cutting section at joints, essentially will be helpful if I have only two forces acting at a joint. Now let us say by the discussion that we just had that we have found out these two forces like that. So that would mean that next I can use this joint, cut that joint, but here again I have three unknown forces in addition to the force that we have just found, and I have only two equilibrium equations. So it will not be possible for me to analyze this using method of statics alone, the equations of statics alone. So this is an indeterminate problem. However, if I take this question, the present question, if I take this question, if I take, and if I cut a section at this joint, so I will be able to see that I have exposed two forces and one 4.67 that is already known. So I can directly apply sigma fx equal to 0, sigma fy equal to 0, and I calculate for the unknown. I can easily calculate the unknown forces. So this implies that I would have to go joint one by one. I have to go from one joint to the other consecutively applying this. So that is what a method of joint is. Method of joints is taking one joint at a time and solving. Now this gives us the liberty to calculate two unknowns because this has only two useful independent equilibrium equations per joint. Instead of doing this, if I could take a section something like this, let us say, if I take a section like this and I pasted it here. So what have I done now? Let me take this again. Yeah. And I put it here. So what I have done now is I have exposed this force. Similarly, this force also gets exposed and this also does. With the understanding that the extension of this is this joint D. So here I no longer have a concurrent force system, which implies that for this free body, I have sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0. All these three can be useful for me to solve for the problem. Now I can see that there are three unknowns which I have exposed here, and I have three equations, so I can easily solve for them. So in a way, method of sections, or rather method of section going through a non-concurrent force system, is it gives us one additional equation to solve. So that is what is a method of section, which implies that it is more general in the sense we can cut anything out and we can analyze that, provided that there are three forces that get exposed. Why? Because we have only three equilibrium equations at our disposal. There will be some special cases where we can also cut four members and reveal four forces out of which two are collinear, which are discussed in the lecture, but those are special conditions. Otherwise, in general, when we take a section, if we reveal only three forces, that is the maximum we can solve with the equilibrium equations available at our disposal, which are sigma fx, sigma fy, and sigma m equaling 0. So that is what method of sections is. And one advantage of method of section in general is that you needn't go from one joint to the other. If we were to apply method of joints here, first we will solve for this, then something else. So progressively we will have to move. But this question is asking for us to find out the force in this member and the force in this member. For that, if we go by the method of joints route, it will be very cumbersome and time consuming. Instead, we will choose to solve it using the method of sections. I will discuss it how that is. So I hope that the explanation is clear. If there are any questions, you please bring it up. Otherwise, I'll go ahead. Okay, now, yeah, yes, yes, yeah. Yes, we can. Only thing is if in an indeterminate truss, if you use method of sections and you cut a section such that you have exposed four forces, then you have four unknowns and you have three equilibrium equations at your disposal, which means you will get an equation. You will get a relation between two forces and not unique values. In such a case, you will have to either bring in another equation from deformation point of view, or you will have to stipulate one force in order to get the other. So that will be the only constraint. There are special cases where there will be forces which are pointing towards each other, in which case, even if you take moment about one point, you can nullify the effect. But those are special cases. It cannot be generalized in that sense. No, both you can use. It depends on how many unknowns are there for that joint you take. Let us say you have a joint which has four members connected through that. Even if you take a section through that, four members means that there are four unknowns, essentially. Four unknown member forces that need to be found. If you take method of joints, you have only two equations. So you cannot uniquely solve for those four. That is the issue. Similarly, for method of section, if you cut a section uh, more than a joint, if you cut a section through members and it reveals essentially three forces, in such a case, you have three equilibrium equations at your disposal and you can solve it. So that is a determinate problem. In an indeterminate problem, if you are able to take a section which reveals more than three forces, but still you are able to solve with equations of statics, you may as well go ahead and do it. But those cases will be less, is what I'm saying. I don't know if I've successfully answered your question. If not, you please follow up question, pose your follow up questions. It's clear. Okay, okay, fine. All right. Okay, so first thing is we need to find out member forces in these two members. Now let us look at the first question. So the magnitude of support reaction at joint A. Joint A, we saw it had AX and AY. So essentially the magnitude of A, let me call the reaction at A as RA, is essentially root over AX squared plus AY squared, which is nothing but same, only vertical exists, but I'm doing it for the sake of completeness. Other than this, we need to find out member forces in members Kj and Ef as we have highlighted here. So let us see how to go about doing that. Now let us say that I took a section like this. Okay, I already have. Say I have taken a section like this. I have at A, I know this is 4.67 kilonewton because we have solved for it. What else is there? I have a force that gets revealed here, here, and here. This is K, this is L. Okay. Now another point is that these two, if I extend them, I'll get this joint as joint D. This is joint D, and this goes on. So it's like this. Now another convention is the best recommended approach is that you initially consider all the members to be in tension. Meaning we have seen in that in this question we have seen, yeah, in this question we have seen that when we have a force that is shown to act away from the member, essentially it implies that the member is in tension. So initially when we draw the free body of the cut sections, the forces that get exposed, we will initially consider them to be in tension and label them to be pointing away from the joint. If it happens to be that the force in the member is compressive, then our answer will naturally reflect that in the form of a negative sign. Now we will assume initially that all the forces, all the member forces are in tension. So if this is the joint, I have put a force that is pointing away from that joint. Here I have put a force that is pointing away from the joint. This member is not cut by the section. So the force in that member doesn't get revealed. It doesn't get exposed. Only the cut members, the forces get exposed. Now this ED member, it is connected at joint E and I have put the force away from the joint. So my initial hypothesis is that all these member forces are tensile and I have considered that as per the convention and I have labeled them. If it so happens that some are compressive, my mathematics will guide me. So I hope that that is clear. It's the recommended approach to proceed. Okay, so I have this. Now I can take the moment about any point in space. I have sigma fx, again I have sigma fx equal to 0, fy equaling 0 and sigma m equaling 0. These are the three equilibrium equations I have at my disposal and this can be applied to this free body where I have three forces revealed. Essentially, let me also label these forces. This is F DE, let me say. This is F K D. This is F K J because here the joint was called K. I hope that you remember that. So this is K. Okay. So if I, what could be the shortest route for me to get Kj is what I need to see. Let us say that I have this extended like that and I have joint J here. I have a joint J somewhere over here. Now if I were to take sigma m about J equal to 0, what all forces will contribute to that? Essentially Kj passes through J, so Kj will have no contribution. FDE does not pass, so it will definitely have a contribution. So will FKD. Now out of the three unknowns that I need to find out, or the three unknowns that have been revealed, the unknown which I want to find out is passing through J, so it doesn't have a contribution, so it will not appear in the equations. And with one equation, I will have two unknowns, which means this would not be a wise choice to select J. Okay, instead if I select D, let us say if I were to take the moment about joint D. Now what will happen is I can see that FD passes through D, FKD also passes through D. So it's a concurrent force system in terms of FDE and FKD. So those don't have any contribution. What else will have a contribution? I will have a contribution for FKJ and nothing else. So just one equilibrium equation applied up at the appropriate joint is able to give me Fkj in one single equation. So this will be a wise thing to do. So let us do that. So let us add the moments about D for this free body. Now I know that this will have a clockwise contribution at D. These forces will have anti-clockwise contribution at D. and this force will also have a anti-clockwise contribution at D. These two do not contribute. So signs we will put accordingly. And we're keeping in mind that this is 2 meter and this distance is also 2 meter. Irrespective of where I have cut the section, I may as well have cut the section here or here or here. Ultimately, I'm taking the moment at joint D. So that is the distance I need to consider. So I hope that that is clear. So let us sum this up. So I have minus 4.67 into sum total of this, sum total of this actually, which is 8 meters plus 1, this force, into this distance, which is again 8 meters plus 1 into 6 plus 2 into 4 plus 2 into 2. Now we have accounted for all these forces, all the vertical forces. Now we have to account for this. So this distance is given to be 2 meters here. So we can take that as F Fkj into 2 equals 0. So can we calculate Fkj from here, what it comes out to be? Let's do that. So it comes out to be 5.68. So this force comes out to be 5.68, which is positive. Positive does not imply tension. It only implies that our assumed direction is correct. And since our assumed direction is tension to start with, force in member Fkj is force in member Kj is tensile. So this is very important to remember. I hope that this is clear. Okay, now that we have calculated Fkj, which is 5.68, let me write it down here. Where was that? So this is 5.68 kilonewton. Our answer says just report the value if it is in tension. So that is what I'll do. Next is force in member EF we need to calculate. So let us see it here itself. So member EF is there, and then and if I take a section like that, and if I take moment about F, we just took moment of, okay, it was F instead of D, is it? Okay, sorry. This should have been named F. I'm sorry about that. This is not D, but this is F. Moment about F. So it's a small this thing. I suppose you can bear with that. Anyway, the point I was trying to make is we just took the moment about F and we saw that force in member EF essentially did not contribute to any moment because it is concurrent force system. If we need to find out the force in member EF, then we need to calculate the moment about some other point where the contribution would be non-zero. So if I take J, if I take the moment about J, I can see that EF will have a contribution. KJ will not have a contribution because that is passing through J, but KF will also have a contribution at J. So I will have single equation, but I will have two contributing forces. It is not that it cannot be solved. Once we take that, we can do again sigma fx, sigma fy and find that out, but it will be a longer procedure. But we must note that there is no convention that we should cut section only from the left. We may as well cut section from the right also. So let us see what happens if we take a section like that. Essentially, we will be exposing this force, this, and this force. So in such a case, with these three forces exposed, this is when I take a section like that. I will expose these three forces. Now I am able to see that if I take moment about K, this will not have a contribution. Kj will also not have a contribution, but Ef will. And Ef is the force that I want to find out. So this will be beneficial for me. So in that case, let us go about taking a section like that and solving it. So let me take a section like that. Okay. So we have calculated Iy here. So I'll replace it with Iy. Iy came to 5.33 kilonewton. And we have already calculated the force in member Kj. But it won't matter because we are essentially not, it will not have any contribution. And I have a force like that. This is force in member EF. This is force in member KF, KD. See here also, I had put it as KD, it is KF. And this should have been FDE. Because this joint is F and not D. I hope that you can bear with that. And I have this as FKJ. If I extend this line and this line, I have this joint. This joint is K. Okay, so far so good. Now let us take moment about K equaling 0. We'll again see that F 5.33 will have a clockwise contribution now. It will have a moment like that because R and this is F. So R cross F is clockwise. These forces will all have anti-clockwise clockwise contribution. Sorry, this will have a anti-clockwise contribution which will be positive. These will have a clockwise contribution which is negative. FDE again, this is R, this is F. So R cross F will be anti-clockwise. And these two forces are passing through K, so they will not appear in the equation. We know that this is 2 meters, this is 2, this is 2, and this doesn't matter. So in such a case, we can write this as 5.33 into, okay, yeah, so this would, into this distance, which is 6, minus 2 into 6, minus 1 into 2 plus 4, because I have summed up this and then separately taken this. And then this is also 2. So I will have plus FEF into 2 equaling 0. So force in member EF is, we can calculate this. It comes to minus 6.99 or minus 7 kilonewton. So force in member EF comes out to be minus 7 kilonewton. So let me copy this again and put it here. So this is negative. This does not imply compression. It only implies that our assumed direction is to be reversed. And since we assumed it to be tension, we need to reverse it and it will be compression. So I hope that this is clear, and if there are any questions, please ask. So this essentially this method of sections I have covered in this problem. So in the application part or anything, if it is not clear, or if any part needs to be explained in Hindi, or there was some other issue, you please raise it now. I'll be more than happy to do that. If it is clear, I'll move on to the next problem. Okay, I take it that this is clear. So let us look at this problem. So we have seen one on method of sections. Let us see what all we are asked to do here. So this is the question, and looking at the question, we can see what all is asked. Magnitude of reaction force at E is asked. Okay. Then force in member AB, BC, AD, AB, and AC. So which are all the forces? AB, BC, AC, and AB. So these are the four members where we need to find out the forces. So initially, let us go about solving this with method of joints and see what all can be done. So at the first instance, it appears that there are no dimensions given in this question. But we know these two angles are 60 degrees and this is given to be 30 degrees. Now one thing we should note that if a particular truss is scaled in the sense that if I take this truss and I make it this big, or I take it this size, whatever be the size, once the angles are preserved and the forces applied are the same, the force in the members essentially remain the same. So it is immaterial of the scale because of the angles being preserved and the force applied being same. So in such a case, let us attempt to solve this without the dimensions and see if we can indeed do that. Now we are able to see that this is 60 degree and this is 60. So we know this has to be 60 degree, which implies that triangle ABD is equilateral. What that implies is these three sides are equal in length. So let us take this one side to be L. So this will also be L and I have this distance as L. Now another point for an equilateral triangle is a perpendicular drawn from one of the vertices will equally divide the other opposite side. So what that implies is this is L by 2 and this is L by 2. Okay, if DC is L by 2, from triangle EDC. Essentially this triangle, if I know this to be L by 2, can I calculate this? Because this angle is given. So I have tan 30 is ED by L by 2, or ED is L by 2 tan 30. So what we have done here is we have assumed one of the dimensions and we have calculated the length of all members with respect to that dimension. In that case, this will be L sine 60. So it will be root 3 by 2 L. Okay, so far so good. Now let us take this section and we have to first calculate the reactions. So the first step is to draw the free body diagram. So let us draw that. This is joint D, this is E, fine. And we can see that we have a roller at joint D and we have a pin support at joint E. So there will be a vertical reaction, call it EY. There will be a reaction like this, call it EX. And then at the roller, there will be another DX. Let us consider this to be the X direction and this to be Y. Okay. So if we apply our equilibrium equations, Fx equaling 0, we get Ex equaling minus Dx because there are no other horizontal forces. So this is one equation we have got. So once we know one quantity, we'll know the other. But even by inference, we can see that this force is pointed downwards. So essentially, these applied forces will try to rotate the truss like that. But we know that the reactions or the pin and the roller are keeping it in equilibrium. So if the applied moment is like that, then the reaction moment would have to be anti-clockwise. We know that both are equal and opposite, right? So what happens when we have two forces which are parallel and equal and opposite by this constraint? It essentially generates a couple. So that couple will counter the effect of these two forces. So with that background also we can see this. So this couple, the reaction couple that will get formed by Ex and Dx. Ex and Dx, we have assumed that it is pointing in the positive x direction. But our equilibrium equation has given that Ex is negative of Dx. So first, let us correct that. Let me take this to be Dx instead. Following this equation, I have corrected the direction of Dx and keeping Ex the same. So now I have a force like this, I have a force like this. So this will create a couple in the anti-clockwise direction, in the clockwise direction, as I can see. This will be R, this is F. So R cross F will be a clockwise couple. We are able to see that the force system that is applied, if we take a moment about this point, so this is R, this is F. So this creates a clockwise moment. Similarly, this force also creates a clockwise moment. So to counter this, essentially our direction needs to be reversed. So what that implies is dx would have, when will we have a couple in this reaction couple in this direction? When dx is applied this way and ex is applied that way. So with that background of understanding, let us reverse this. Dx, Ex. Following this, and the sense of couple that it has to form. Okay, now we need not do all this, it will come from mathematics also, but simply doing it in a mundane way, I thought it will not lead to any enhancement of understanding. I suppose if we look at the same question in different, every which way that we can, I suppose that it will give us new ideas. That is why I am approaching this reaction from a different approach than we did earlier. I may as well have labeled it in the positive x direction, gone about solving sigma fx fy mz, and I would still get to the same answer, but that will not give me any additional insights or give me another via media to quickly solve problems. So that is why I'm taking this route. If you're not able to follow, once I finish this, if you're not able to follow, I'll try to solve it threadbare as we did for the previous problem also. Or perhaps that is something you can attempt on your own and get back with your questions. I hope that you can bear with it. So we have dx like that, ey like that. So this creates a clockwise couple, and these two forces creates a this creates an anti-clockwise couple, and these two forces create a clockwise couple. Okay, so about D, if I take moment of these two forces, what will that come out to be? Of the external loads, if I take this, it will be minus 5 into, we noted that this distance is L and this distance is L by 2. So it will be L plus L by 2 plus the reaction couple. Let me call that MR. Let me call that couple MR, which is created essentially by these two forces, which are equal, opposite, and placed this distance apart. What is this distance? It is, we have calculated that as L by 2 tan 30. So MR is a reaction couple which is equal to dx into distance L by 2 tan 30. This may well be Ex also, only it will be negative. So I hope that that is clear. Dx is in the positive direction. So a couple like this would be dx into this distance. This distance is L by 2 tan 30. So that is why I have written it like this. Dx. What is given? dE is given in the question. Oh, I see. Okay. I did not note this, but even without that you can solve. So, okay, let us go about doing that. Because you are able to see that L is in the left side as well as right side, so it will essentially get cancelled out. So I was just approaching from another end. I did not note that it was given. Fine. So it will be minus 5 into 3L by 2 plus dx into L by 2 tan 30 equaling 0. So can I calculate Ex from here, dx from here? So essentially L gets cancelled out. So I have 2 by L tan 30 into 15 by 2L. So this dx comes out to be, I can just remove the 2's. I can remove L. It is L 15 by tan 30. So it comes out to be 25.98 kilonewton. Okay, now that we have got dx, we know Ex is minus 25.98 kilonewton. That was when we had marked that in the positive x direction. Okay. Now sigma Fy equaling 0 we can easily see that this force has to balance the sum of these two forces. So Ey has to be 10 kilonewton. I needn't go and write it. So Ey is 10 kilonewton. Now that we know this, the magnitude of reaction at E will be root over of this, which comes to 27.84 kilonewton. So we were asked, this came to 27.84 kilonewton. K small. Yeah. Okay. So based on the relations that we derived, if L by 2 tan 30 is given to be 3, if this quantity is given to be this 3, which I didn't notice, then we can back calculate L easily. But we'll solve this with L. No issues. Okay. What is the member force in AB is what is asked. So let us consider this joint. Now I'll have a force like that, and I'll have force like that. This is force in member AB. This is force in member BC. And we have seen that I have taken both of them to be pointing away from B, with the understanding that these represent tension. If my answer comes out to be positive, the directions are correct. So at a joint, I can apply two equilibrium equations. So let us apply that. Gives me minus FBC minus FAB cos 60 equaling 0. Sigma Fy gives me so FBC will be minus FAB cos 60, is minus of minus 5.77 cos 60, which is half. So FBC comes out to be plus 2.89 kilonewton. So this is straightforward. I don't want to delve much into this. It is just arithmetic, which you can do. So I have calculated this to be minus 5.89 kilonewton. Force in member FBC is plus 2.88 kilonewton. Sorry, this is 5.77. Sorry about that. Yeah. What is the ratio of the force in member AD to that in member AB? What is asked is FAD by FAB equals what? So one way is that we go about solving this and doing, or we can just do it by inference. So let us see how that is. If I take the free body diagram at joint A, I essentially reveal three forces. This is FAB, this is FAC, FAD. So this is my free body diagram of joint A. Now from symmetry arguments, I can say that FAB and FAD are same, because sigma Fx equaling 0 implies FAB equal to FAC. So the ratio is essentially 1. What is the force in member AC is what is asked. So from here, if I see for this joint, if I take Fy equaling 0, I know that this angle is 60 degree. If this is 60, then this also has to be 60. It gives me FAB sine 60 into 2. Because of this, I'm taking into 2 plus FAC equals, sorry, minus 5 equals 0. So FAC is 5 minus 2 FAB sine 60, which gives me which is nothing but this came to minus 5.77. Oh, 3. So it is coming to 15 kilonewton. And it is positive. I needn't say what that means. It means that our assumed direction is correct. And since we have assumed it to be pointing away from the joint, it is in tension. It makes sense when we are pulling it like this, it would naturally be in tension. So, okay. So this comes to FAC is 15 kilonewton. All right. Then how many zero force members will be there in the given truss if the joint at if the load at joint B is removed? The thing, this question, we must ensure that we are talking about a situation where this force is removed. It is not for the current present configuration. So first let us make a copy of this and try to remove that force and see. So this is my truss and this force I have removed now. So now the question that is asked is how many zero force members are there. So let us go about by after recalling our constraints that need to be checked for zero force member, we are able to see that joint B has two members which are non-collinear and it is free of any force. So this is a zero force member. This is a zero force member. So we may as well, okay, let it be. These two are zero force members. Now we can see that at joint A, we have one force pointing downwards. So one force is like that, one force is like that. And since BA is 0, it is already 0. So we can imply from these that when these two forces are collinear, this force has to be 0. So this will also be a zero force member. Okay. Now we can see that force AC will be 5 kilonewton. So it will be in tension. So it has to be pointed away from the joint. So this also has to be pointed away from the joint. Now essentially we are looking only at this truss where a force at C is applied like that. This member is not there because it is a zero force member. So we have a triangle where we have a force applied like that. And this is a roller support. Okay. So if this is a roller support, we know that a reaction will be like that. And we have one member like this. So if these two are collinear, then the member in the third force is 0. So this also becomes a zero force member. So essentially, if that by removing just one force from our system, we can see that so many forces in the members goes to 0. So from one, just by removal of one load. So we must keep in mind that zero force member doesn't mean that it will always carry zero load. Essentially, it depends on the load configuration that we are considering. So I hope that this is clear. At this joint, if we see, we have a force applied like that. So if we cut a section, we will have two forces. This force vertical component will have to balance this, and the horizontal component will have to be balanced by force in member CD. That we can do like we did for the other problems that we can easily do. So are there any questions based on what we discussed? Anyway, we are able to see one interesting thing is that this is a redundant information. Even if this is not provided, we are able to solve for the unknown forces. So that is an interesting thing to note. What that implies is these angles are enough to preserve the geometry and to define how force distribution will take place. So either this or this could have been omitted, and we can still find out the member forces. So it is redundant information. So there will be 4 zero force members in the event that joint B is free of any force. So are there any questions at this juncture? I hope what I'm explaining is clear. So और जो हिंदी में पूछ रहे थे, मेरे ख्याल में मैंने आज काफी धीरे बात किया है और एक्सप्लेन किया है, तो अगर आपको कोई चीज ऐसी है जो समझ में नहीं आई और आप चाहते हैं कि मैं उसको हिंदी में बता दूं, तो मैं बता देता हूँ। आप बता दीजिए कौन सा पार्ट नहीं समझ में आया, अगर ऐसा है तो। अगर क्लियर है तो फिर देन फाइन। Okay, I take it is clear. Any other questions you have from this week or previous weeks or whatever we discussed so far? If there are any, you please bring it up now. Okay. Yeah. 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 No, see, including equilibrium would be total number of equations. So if by equilibrium we have three equations, let us say, at our disposal. For example, for this joint, let us consider this joint. We have three unknown forces here, which get revealed when we cut that joint. So we have equilibrium equations that we have for this joint is two. So how many additional will be required to uniquely solve? From that you can figure out, right? The total number of equations required is three because there are three unknowns. Equilibrium provides only two. So additional implies that over and above the equilibrium what is required. Okay, yeah. Yes. Addition, yes. I'm just explaining the terminology to you. Total number of unknowns implies we need total number of equations. If from the total, if we take out equilibrium, the rest of them are additional equations that are required. So if it had asked for the sum total, it would say total. Otherwise, it will just say additional. Yeah, yeah. Okay. Anything else? Are there anyone else has any questions? Is it clear what I'm trying to explain? Could I just get a confirmation on that, or clear? Okay. What about निशांत and शुभम? Is it clear? कुछ ऐसी चीज है जो समझ में नहीं आई जो मेरे को फिर से समझाना है? अगर कुछ है ऐसा आप चाहते हैं कि मैं हिंदी में बता दूं तो आप बता दीजिए, मैं भी समझा देता हूँ। या क्लियर है तो फिर ठीक है, बहुत अच्छी बात है। Okay, anyway, I take it that it is no clear. Okay, fine. Yeah, actually today I spoke a little slower, so I suppose that even English explanation is okay. All right, so yeah, let us quickly take a look at this question. I won't solve it fully, but let us just analyze it with whatever tools that we have developed so far, the understanding. Let us see what will happen. Consider the planar truss shown. Enter the magnitude for each and every each and every member, the magnitude of force that we need to report. And it is the magnitude that we need to report. Please keep a note of that. In the question, if it says, if in a question it shows this note that, where is that note? There is a special note, right? If this note is shown that if it is negative, report it in this fashion. Otherwise, if it is tension, report it in this, compression, report it in that. So that we need to ensure that we follow. But in the last question that we saw, we have just been asked to report the magnitude. So no matter if it is tension or compression, we will report it as it is. So in case we need to do that, let us just quickly take the free body diagram of this. I have a roller at this joint, which is D. So it is dy, and I have a pin at A. So this is AX and AY. So simply by sigma fx, I can see that AX would have to be minus 30. So I need not even write this. I'll just put this as this as 30. So I have got this. Now if I take moment, it will be contribution of this moment will be 90. Contribution of this moment will be 60. 90 plus 60 is 150. And this distance I can calculate. This is another, if this is 3 and this is also 3, so it will be 150 by 6. So I hope that is clear. So it will be 25. So essentially these two forces about A, if we see, they are trying to rotate it in the clockwise direction. So dy will try to restore that by applying a force like that. So essentially it is dy into 6 and 150. So this will come out to be 90 plus 60 by 6, which is 25 kilonewton. And if this is 25, the top force is 5, then this would have to be, if this is 25, that is 5, then this would have to be minus 5. So this will be pointing downward. Why this points downward? Because this is getting pulled. So this is trying to lift this joint up like this. And this force is trying to prevent that. That is why AY will essentially be pointing downwards. So this will be 5 and we have this as 25. So now we can apply the same thing. First thing is, let us check for zero force members. So at joint C, I am able to see that 30 kilonewton point is parallel to the force FCB. So essentially this will be a zero force member. This will take the entire load. This won't be a zero force member. This will take the entire load and I'm able to see that this is being pulled. So force in BC would be 30 tension. So now that that is out of the way, I know here it is 30, here it is 20. I can solve for the rest easily. So once I get this force, I'll just take a component which needs to be balanced and I'll be able to find it. So this I'll not solve as of now, but I hope that with our discussions, you'll be able to do it easily. So you can just take this as a perhaps an exercise problem if you're interested. So other than this, I suppose we have today what we have covered is we have covered the method of sections, the method of joints, and we have seen that the method of joint is essentially a subset of method of sections where we get only two equilibrium equations because of the concurrent force system. So we saw a brief into what purlins are essentially. These are bending members. These are beams which transfer the load to trusses. And then what are the constraints that need to be respected by a member to be analyzed, for it to be analyzed as a truss. So these are the constraints. We saw the convention, what happens when we see things with respect to the pin. And this is the convention that we'll follow when it points away from the pin. We'll take the member to be in tension and compression in the other case. And that is how we will essentially be marking forces and solving for unknowns. Other than this, we saw what are the conditions for finding out zero force members. So when we start a problem, it is easier for us to identify the zero force members first so that we can remove them from the analysis and carry out the analysis only on the rest of the portion. This question essentially, we saw that we had to find forces in a member which was not close to the support where we will essentially find the reactions first. So we cannot proceed one support at a time, one joint at a time and come to joint E for us to solve for EF. So we need alternative methods, which means we need a section that essentially has a non-concurrent force system, which is what we saw as the method of sections, which we took. We saw which joint to select for which force to be calculated so that our calculations become easier. So with practice, you can see this, you can get the hang of this. And this problem we solved where we saw that the dimensions, one of the dimension, even if it is not given, although it is given, even if it was not given, we will still be able to solve this problem. And we solve for the reactions from an alternate method instead of going by a regular route. So we need to employ all these techniques together in questions so that we can solve them quickly and accurately. So with this, I suppose we'll end truss analysis. Next week, we'll look at beams which carry transverse load and we'll look at how to draw shear force and bending moment diagrams. So till then, if you have any questions now, you can raise it now or you can ask in the forum. Other than that, I have nothing more to say today. So I'll see you guys in the next session. Okay, guys, then I'll see you next week. In the meantime, you keep your practice up. And if you have any questions, you please approach the forum. And yeah, so I'll see you guys next week. Thank you. Thank you for attending.